So indeed, we are using already for 25 years in the beginning mainly the Mark software, but meanwhile also use other software features. So this one. So I will give you a brief view on the how we use computer engineering simulation for nano-electronics and digital systems in imec. Just very briefly, what imec is, if you don't know it, it's a large research center in beginning in Belgium, but meanwhile we have centers. We have two centers in Netherlands, with Holstroom and one with Wageningen, one Planet, also in another region of the world. And we in Belgium we have an infrastructure, clean infrastructure, world class, 12,000 square meters, where we basically do the scaling, mainly the scaling of the signal scaling to go to the most advanced nano-electronics. But we also have do a lot of many different application domains. You can see it: health, mobility, cities, industries, energy, education, and agri-food. And in the field of the digital technology platforms, we also do a lot of work in networking, digital privacy, and security, and also the software and the management skills. So I will mainly focus on I would say, this domain here. More on the technology side. So why do we use simulations, CAE simulations? It's basically to support the design of a piece of electronics. And the objective is to answer these typical questions like if you have an electronic system, can be small, can be large. What will be the maximum temperature due to the heating of the processors, the power components, or just due to joule heating inside wires, very tiny wires with a large current. Also, for example, if a product has to be qualified, space or automotive qualified, before you make the first prototypes and do the testing, first do the simulations. And sometimes also we do tests on we try to explain failures that we see that are seen in the field, like fraction in solder joints. After dropping several times the handheld application, the simulation can reveal that there is an overstress in some locations, and after that you can start also redesigning the structure to have a better, to avoid these kind of failures in the future. Okay. Also important to mention is that we have very broad scale that we apply these simulations, going from micrometer or even sub-micrometer to the very tiny metal lines connecting all the transistors, which is we call the back end of line, up to the small connections between chips, wire bonds, micro bonds. You have component level studies, board level studies, and also assembly. And then you can end up with I would say, several DC meters of size of the board. And sometimes you have to cover the complete thing. So probably not always, but sometimes you, for example, thermally, it can be that you want to know what happens locally in the transistor, but you still need to know how global cooling is of your system. Same for mechanical, if you have vibrations. You can have failures in this level, but you have to translate the vibration at the global level to the local level. So this is quite often quite challenging for us. Here I have a few use cases, just a few of them. I could have many, many more. But the first one is a cooling device, very advanced cooling device for processors, GPUs, CPUs, and so where we used the Cradle software to optimize the structure. And so it was a project where for processors to be used in autonomous driving cars, level 5, and So a lot of power is dissipated. So you can understand 300 to 900 watts. Automotive means that the temperature can be 65 degrees of the liquid. It's just which is in outside temperature. And the temperature of the chip should not be higher than 95. So a very small window, a lot of power. And therefore we were investigating like jetting a liquid, a polyliquid directly to the backside of the die to get the heat away from this. And the device that we use for that is a 3D printed device. And the advantage of the printing is that you have can shape the channels such that you have an optimal structure that it has minimum pressure drop. So it's not only maximizing the heat transfer that you want, but also minimizing the pressure drop in the structure. You see now some simulations. And so you start from a CAD structure, CAD model. You create a CAE model, which is with SC flow. In this case, with the polyhedral mesh. You see here the flow lines on the right side. So objective was to redesign the structure, maximizing the heat transfer, also trying to have cooling all over the chip, not very localized in the center, for example. Also, the corner areas should be cooled as good as possible, and also minimizing the pressure drop. So optimization is still in a kind of manual way, so it's not like an Odyssey-based optimization. So maybe that's something can be useful in the future. And so, just to see here a sample, you can have a look at it. So this is the actual printed sample, where we already have done the first test with in real structure. So the next example is the 3D stacked devices in microelectronics. So you see here a movie. So instead of having everything all the logic processors and the memory all in one chip, we prefer, or the industry prefers, to have them in separate chips, and that you put them in kind of multi-chip modus together, and to save space, to make it as compact as possible. You don't put them aside, but you put them in a stacking mode, so you're stacking them. And as such, so you have like optical chips, processor centrally, and then a lot of memory dies stacked. So you do this in a 3D, that is what they call 3D technology. So to maximize the compactness of the and also the performance of your structure, because also the connections are very short, so you can also have very high throughput of signals, electrical signals. Yeah. Also, in this research, a lot of mainly Mark is used to perform studies on the stress. So, and it is also done from I would say the component level, but to even sub-micrometer level. And so you see it here. So that's a typical example of such a 3D stacked solution, where we look on what happens, the stresses inside the back end of line structures, the very tiny metal lines next to connecting all the transistors. Also, in order to be able to have connections from top to the bottom, they basically make holes inside the silicon and they fill them with copper. But the thermal expansion is also a large issue, because of the copper is expanding much more than the silicon, and you can also have things like fatigue or damaging the surrounding, or even changing the transistor each other in the neighborhood because of mechanical stress. Also looking on the microbumps, another example where the stresses can be an issue. And at a large component level, because you are mixing a lot of different materials, they're also quite thin. So you can also have like warpage and bending, large bending, which is not allowed. So it's a lot of studies that has been done on such structures, and it is really it's all done not in one simulation model, of course. But it's all the same research that has been performed. And you see here some other examples, just small meshes, but where a complete stack of different chips, and also sometimes silicon substrates and also organic substrates are all together. Okay. The third example is a sensor module. It's a sensor module which is to be used in industrial equipment. And it should also work in a kind of wireless mode, so no electrical connections. So you see here a view and description of this such a sensor module. And simulation model has been created, and this is fully made in Apex software. And the scope was because it's harsh conditions. So mainly there's industrial equipment, so a lot of mechanical vibrations. So you don't want to have this sensor being damaged over time due to these vibrations. So, and the first thing that you look at is the eigenfrequencies to see if it's above the range of frequencies that are applied to the structure. So you can see you can also see in eigenmodes what kind of deformations that you see in at the components. So then the next step is to basically also make predictions of the lifetime of the joints. So, and the first design, as you can see here, its lifetime was first moment was the high frequency was 259 hertz, and then an optimization has been done in design, and then the first eigenmode was increased to 1467, with also much longer lifetime. And so this is, though the first one was already 30 years and also it's probably not really needed much. And the last example is we also use it quite a lot for space applications. Same kind of research. In this case, it was on reliability of the printed circuit boards which are in space. In space, because of daylight and the sunny side or the dark side, it sees every day a strong thermal cycle, and they suffer also the boards. I have here a picture. So because of this difference in thermal expansion between the organic part of the board and the copper, so inside the copper, you can have mechanical fatigue in the copper structures, so causing cracks, and after a while, if the cracks is fully surrounded, then you have no electrical connection anymore, and of course, in space, you cannot repair it anymore. So that's why you really have to quantify as good as possible what is the number of thermal cycles that the structure can survive. And for that, we also used the MARC software. So here in the yellow part is a plastic deformation that it sees during one temperature cycle. And the size of the plastic deformation is, of course, related to the lifetime. Lifetime is related to the size, so we have empirical models to translate this. And here you see an example of a complex HDI and high density interconnected printed circuit board, where you have like a long through-hole vias, but also small micro vias on top and on the bottom to simulate the lifetime. And based on the strains, you can translate this in lifetime. And then we also were looking at successful so far, but also to use CAE and the fatigue tool, the CAE fatigue tool in MARC, which is also featured in Hexagon. But you immediately can have a lifetime as an export to the model. Something that we for sure would like to do. But I think the one issue was with that we could not just add and our own empirical model that we were restricted to some fixed models which are in the software. But maybe that's something we can do in the future. It also would be very interesting for us if this can be included. So some conclusions. So I think we use a lot, already for many years, the software to support the designs of the, and also the technology used in nano-electronics, nano up to millimeter electronics, up to millimeter scale. And what we see as a future challenges, so we partially solved in future features of the software. But I think the first challenge is what I would call multi-X. X stands for multi-physics. It's obvious, but for example, also you start getting questions on having some biological effects. If you have like a CAE simulation of a liquid, but you want to add something, reaction of the particles with to add some physical, biological models. But that's something which is getting interest. Multi-scale, I've shown you, going from very small scale to a big scale, and you cannot always easily zoom in a certain area without taking care of the complete area. Multi-loading, loading is like having a combination of vibration and temperature and mechanical shocks, and do this either in parallel or sequentially. That's also challenging. Also the process flow, more and more need to be added to really simulate a complete process flow. A process flow in our case is like you start with a blanket silicon wafer and you start adding layer and layer at different temperatures. So now it's also quite a challenge to do this in simulation easily. And also more and more we interact with other companies or research centers who are using different software than the hexagon software. Interaction is sometimes needed and it's quite challenging. Then another challenge is the digital twins and compact models, and then it's mainly, it was nicely described in the previous presentation, or the presentation with DC. So I'd also be on to how to translate a complex FEM into a kind of digital twin or compact model. I think it's quite similar. Also modeling with uncertainties. So parameters are not deterministic, so they can vary, process dependent. So to include this in the software, that you don't have like my stress is 112 megapascal, but my stress will be 112 plus minus 17 megapascal. Yeah, so this kind of modeling will be also very interesting. And also was nicely introduced or described by Odyssey presentation is you have simulations, you want to validate simulation with experiments, and now you do this mainly manually, like you watch the two pictures and you see, okay, you try to see if there's a good match or not. But if you do this more in an automated way, so that you even that you say, okay, I just do some measurement on a component, I don't really know what is inside, but I know the deformations. I put this in deformation in a simulation model such that I have a model that can be put in a larger model. That's also, do this in a kind of automated way, that's also what you see as a future challenge. So that's, here I come to the end of my presentation. Thanks.